I want to say a few things about human-robot collaboration. Um, Something that is, as you know, a very important aspect of AI these days. We have seen those five big ideas in AI education, not just in AI education, but in AI. And one of them is the ability to interact with robots. We do this all the time. If you have Tesla, for example, I mean, you saw like interacting with a robot. Um, and they're sort of perhaps not robots, but other tools and devices that you interact with that sort of like have to have the same sort of abilities as a robot. So think about Alexa. I know Alexa is not a robot, but there's certainly some sort of communication going on. Now, what we're interested in here is we're interested in collaborative problem solving, and this is a paper that I presented about a year and a half ago at the Stanford Spring Symposium. And as you can tell, this was some work that I did with some students at the time. They all graduated now and work in nice places, at nice companies. So Michael Crowell, Devin Dong, Walt Panfil, and Adit Suvarna. So let's have a look at what we're doing here. So this is a fairly representative system that gives you a sense of what people are doing when they're working with when they're doing human-robot collaboration. So the problem that we're trying to solve is, or what we're interested in is human-robot collaborative problem solving in a shared space. So shared space is very important. So the robot and the person are in the same space. So this is not like where a person might operate a robot in a remote fashion. So think about some of those things that people are interested in is, there's a robot, I don't know, on a space probe and it's landed on Mars or something like this. So it's still problem solving, it's still collaborative, but it's certainly distant. A nuclear reactor blew up and you have to go in there. So obviously we don't want people to go in there. So a lot of times there's some sort of collaboration between a robot and a human. But it's different, it's of a different nature. So so that's collaborative in a shared space, I'm sorry. And so the idea of collaborative is that ideally the robot and the person are on the same level. They truly collaborate. So it's not that the person tells the robot, do this, do that, do this. But ideally that the robot might say, hey, have you considered those sorts of things? And so we know that the robot does have certain abilities and the person has certain abilities that the robot might not have. And so to a certain degree, we probably want to build on the strengths of each. This one here will be very, very helpful in manufacturing for small to medium-sized companies that cannot afford huge, expensive robots that need to be programmed, that have to have programmers on staff, and that have to be maintained all the time. So that's kind of like what we're aiming for. But healthcare, and there are many other areas in which this is important also. So what we are doing is we're engineering a system from the bottom up. So we don't have a theory that we want to prove and for which we build the system. The objective is we built the system, and if we discover that we need something else, well, we'll figure out what else we need to improve it. Ideally find some existing packages, include them, and if not, build it ourselves. So to a certain degree, that's what IBM Watson did. So they did create their baseline system, and then they studied it and realized it wasn't going to be good enough to beat Ken Jennings and Brad Rutter. So they improved it. And I sort of try to give you a sense of some of the engineering that went into improving it. So they just sort of like looked at things. Does it make it better? Great, let's keep it. If not, let's do something else. One of the things that IBM Watson did is they used UIMA to manage the central information processing tasks. And that enabled them to make a highly modular, or to develop a highly modular system. And so that's the same thing. We're going to do the same thing. So we're developing a very highly modular system in which we can plug in and plug out or modify components very, very easily. So what we do is we call it multimodal because we use two modalities for input. We use gesture as well as speech. And at the time when we developed this thing that was quite unique, we eventually learned of a Japanese company that also uses both modes. And I'm sure there are some research labs that do use more than one mode at this point in time. But at the time, it was very, very unique. So most I attended a conference or a symposium a while ago, and there it was all speech. And so one of the things that they had to do is they always had to go through a pre-processing phase in which they had to name objects. So they had to say, well, that object over there, which is 3 spaces over from the Coke can and behind the Pepsi can, name that one whatever, Bob. And so then after that, they could refer to objects by name. But we felt that was not how people do things in the real world. And again, even after the naming phase, there was no ability to point at things. And we thought that, well, that's what people do, right? I mean, they point things, hey, pick up that block, pick up this block, put it on top of that one. So that's why we feel we're sort of like on the right track here. We are doing things on a shoestring here. So everything is kind of like fairly low impact here. A microphone is easy to get a hold of. The camera too, we actually bought a used Kinect V2 sensor, believe it or not, and somebody had a coupon to buy some of the cables. So we have these 3 inputs, we do some processing, and then we'll act on it in one way or other. So I should tell you that what I'm presenting over here was a prior version of the current system. So this was done by some students in 1819, and I since had a team work on it in 1920, and they all graduated. And I'll see at the end of this presentation, I'll say a few things about the current status of the system. But in order to get an overview, this is perfectly fine. So UIMA is an Apache project. It was developed by IBM. It already existed, but they sort of took UIMA and made it work. They made it robust. And so what does it do? Well, here's an example. So a key component of UIMA is a common analysis object, or a CAS. These are the blue things. And then there are annotators, and annotators are these gray things. They process information. The other thing is it's a processing pipeline. It's not a cycle. It's not a while. It would just start at the beginning, one shot, and you're done. So the idea then is that we initially start with an empty object, and we add things. So each annotator adds things. So suppose we want to do some simple parsing. Here's how one could do that. So we initialize the CAS object. We read a document. Ta-da! We have a text string. So then once this text string is there, we might realize, oh, wait a minute, I have a text string now. Let me run this annotator. So these annotators can, in principle, process at will whenever certain preconditions are satisfied. So then we add the parse tree to those things. So notice that these CAS objects are additive. They could be, I mean, you can also remove information, but we add information. Then we do named entity recognition, so we add that. Then we create an index for some sort of collection, so we add this. We add some structure to this thing. So the idea is it's almost like a whiteboard. We add things, add things, add things. Oh, I have an idea. Let's do this, right? So that's sort of like what UIMA is all about. So what I will do now is I will run you through the information processing in our system as it was about a year and a half ago. So what we do is the first annotator that we run is the one for object detection. And again, we start out with an empty CAS object. And so one of the things that we need to do is we have this camera that looks at our workspace, and we need to identify the objects. And so the team at the time took a white tablecloth, put it on the table so that we have some good contrast for the background. So here is an image of the outcome of the image pre-processing. Everything that is green, so like identifies an image, and the center of the green circle is the perceived center of the object. So again, there's actually a lot of work that went into getting this thing to run, and it runs just fine. So what we do then is we add that information to the CAS object. So here's an excerpt of the CAS object. And so we give each block an ID. We tell it the X and Y coordinates, and the camera space is 3D, so it has actually 3 coordinates, and we record the hue. So notice we don't record the color, we just simply record the hue. So it's all very technical information, just some very basic processing. If we go back to this one over here, we don't do everything in one fell swoop. We do one thing at a time. Read the document, initialize. This is good engineering, right? Check. Parse the sentence. Check. Moving on, right? So that's what we're doing. We're doing just one thing at a time. So, so now after object detection, we have the object colors. Again, that's not quite right. We really have the object hues, and we have the object centroids. So that's very, very important. So the next thing we're going to do is we're going to do language processing. So notice that this can be done independently of the object detection, but in the system that we had at that point in time, we did one thing at a time, so it was very linear. So language processing, we do speech processing, text processing, and then we establish confidence ratings of objects in the domain. So let's see how we do that. At that time, we used Google's Cloud Library speech-to-text services, and we didn't use the Stanford parser at the time. We simply used the string, and we looked for occurrences of words. So we had a dictionary that was added to the code that knew about hundreds of color words. We had so this was a superset of the actual block colors, and then we did substring processing of text to locate one of the color words. So if the text that the user inputted says something about yellow, we're looking for any of those words in the text. All right, so suppose the user said red. So that was added to another class object then. And so again, the outcome of this text processing of color was simply that, oh, I found a color word. Here it is. So the next thing we had to do is we had to calculate the confidence rate. Again, that was very important to IBM Watson, and that's sort of like a key aspect of modern AI systems is confidences. When we looked at logic in this course, we kind of like said that, hey, look, you know, not everything is black and white, not everything is true and false. I mean, there are sometimes, you know, what am I saying here? Variations in the knowledge. We're sort of like mostly sure that something is the case, or we're confident in. So what the team did is they used the hue information to compute a confidence rating. And so the confidence rating represents a degree of match between color word and perceived color of a given word. So this is kind of interesting because I was hoping to find the hues again, but they're not here right now. So this is important because under different lighting conditions, different hues might end up, or the same color might give you different hues. And again, if somebody says orange and they really mean red, red and they really mean orange, we sort of like still have a pretty good match. So that's really important. So at some point in time, you know, we sort of have some confidence. These are the 5 blocks that we had in this particular example. And based on the color words, we're sort of like pretty confident that block 3 is the one that we're interested in, or is the red block. And so we add that. Yeah. So we have object confidences based on language. We have and so that's what we added over here. So next we're going to do gesture recognition. So that's a big deal, as you might imagine. And so we used the Connect. It had some libraries that came with it, and everything is implemented as a C# web service. So somebody is pointing at an object, and so based on the processing of the data from the Connect, again, there's some libraries that make this thing fairly easy or relatively easy. We're sort of like saying, okay, it looks like they're pointing towards this block over here. So yes, they're using the joints as the basis of estimating a vector in 3D space. And again, there's a confidence factor that sort of like gives us a sense of which block might be identified. And that information is, again, added to the CAS object. So based on pointing, we have a confidence of 1 that it's ID, that is block 1, and a confidence of 0.75 that is block 2, and a confidence of 5 that is block 3. I should tell you that it's kind of really hard to evaluate the pointing data. And so the confidences are sort of a little bit more all over the place. All right, so we have object confidence based on language. We have object confidence based on gesture. And so the next thing we need to do is we need to take all this information and so like see what we have to aggregate the information. And so how we do this thing at that point in time is a simple product of normalized confidence ratings. And so we just sort of like calculate a number. And so based on that, we add things to the CAS object. So now we normalize things too, so that one component can take over. So block ID 1, so here's the overall confidence. Here are some additional, the normalized pointing confidence, the normalized text confidence. And so these are some pieces of information that we have. So notice that I left out some of the other stuff. So in this particular example, block ID 2 has twice the confidence as this one over here, but it's still pretty low. So we have the aggregate confidence, and then the next thing we're going to do is we're going to give some feedback. And so the feedback, we pretty much say, got it, or I didn't understand, please start over again. Okay, so we acknowledge that the robot has, say, high confidence. And then if it doesn't have high confidence, we're going to ask for clarification. So we might say, I found it, or I'm having difficulties distinguishing between the blocks, please try again. So this is sort of like the first part of engaging in a dialogue, right? Where the robot doesn't just sort of like, say, I think they mean this, let me just do that. But where they sort of like say, geez, I think you mean this, but I'm not 100% sure. So this unit is based on this final processing, where we sort of like believe that ID block with ID 3 is being selected. So if we have high confidence, then we put a 1 in here and zeros everywhere, and that's a block that would be modified. So in that, the positive feedback then would be, I have found the block, I will try to pick it up. Ta-da! So that's sort of like the pipeline as it was about 1.5 years, 2 years ago. So at that point in time, we hadn't integrated the system with the Sawyer robot yet. You may have noticed that we actually we didn't use cubes. We sort of used some fairly flat pieces. We used a substring search, and since we replaced it with a parser, and we also added a naming unit. So eventually we want to do some fairly complex stuff. And so the planning, we didn't really have any planning at the time. We didn't have memory. And so notice that something like this, a robot can't do it. Well, a one-armed robot cannot do it themselves. So you really have to have two people who sort of like do this thing together. So what have we seen? Our CAS objects, which are additive, house information about the problem space, multimodal input from the human, and confidence information. Eventually, once we sort of like have the ability of planning, we also have knowledge of how to solve a problem. So I should tell you that this has been a project that has been ongoing for a while. So this team took over from a team that worked in 1819. It was James Gibson, Lewis Kelly, Remy Bibulka, and Kieran Grobel. Also, in the beginning, this project was a collaboration of Dr. Barry, Dr. Shibur, Dr. Wink, and myself. So what's the current status of the system? So this is the status as of the end of the winter term of earlier this year, 2020. So 2019 to 2020. So we have made some changes to many of the units. So we actually use a different speech-to-text component and a different text-to-speech component. We now have the memory import. I'll say a few things about that in a moment. And we have memory storage. And so memory import enables us to name blocks. We can say, name that block to the left of the red block, Bob. And then later on, we can say, move Bob, or something like this. So that's the memory import and storage, so we can name blocks. You also notice that I'm indicating here some of the parallel processing that's going on now. So we have speech to text, which again, has to happen before NLP, but we also have object detection and object gesture recognition. So all three of them kind of have to happen very early on, and they're all independent of each other. The NLP unit now is considerably more complex. It does use the Stanford parser to do some basic processing. We have color recognition. That's the same as we had before. But now we also have spatial relations. We can deal with spatial relations very easily. So we can say, pick up the block to the left of the green block. And so what we have over here is, based on the objects, we sort of like generate possibilities, if you wish. We sort of like parse the space and realize that there's a green block to the left of a red block. There's a green block behind the red block. Those sorts of things. So over here, we just like generate spatial relations that exist among the objects in our domain. Over here, we actually use the information that we generated over here, also the color, and as well as the NLP unit to sort of like identify blocks. So the idea is, if somebody says, pick up that blue block next to the green block, or to the left of the green block, we then use all this information over here to sort of like process and identify which block we might be referring to. And so that's what this unit does. This one over here aggregates the confidence. Again, there's some information that we're going to combine. There are some other things that happen in the NLP unit. And so we now have confidence values in each of those in the blocks that is being moved. So then we have some interesting things that sort of like go into context a little bit. So we have perspective transformation. So the camera sits opposite of us. And so if I tell the camera, pick up the block, to the left of the green block, well, the camera obviously, it has to be the right then, right? So that's some stuff that we do over here where we do perspective transformation. It's actually a little bit more technical than that. So the idea is that our camera sees things in terms of where the blocks are in the workspace, its X and Y coordinates, and then the robot has a different coordinate system. It has its own camera. So in the perspective transformation, we're actually transforming X and Y and Z positions from our camera, from our Kinect, to that of the robot. That's what we're doing over here. Then we have the communication unit that determines what to communicate back to the user. And then we have text to speech over here where we actually speak it. Some over here we like do some cleanup. If we have to store something, we do that. Memory storage will be added to some file that's persistent that we can then load again over here. And then we have the command unit that sort of like issues the actual commands to the Sawyer robot using the ROS operating system, the robot operating system, which is called ROS. So that's the current system here. I wrote up a few things, some blurbs about each of these components. So the NLP unit, we extract commands as a pickup or build a tower or naming a block. We pick out block colors. We pick up relative locations of blocks. So again, this was a huge step forward for us from text processing, string processing to using objects. So this is sort of stuff that you are working on right now. I'm going to ask you to work on the HRC project for this course. I should tell you that there is a senior research project going on where the team is sort of taking the NLP unit yet to a new level, and they're making excellent progress on that. And so it is going to be a much more robust system where we can process things in a much more robust way. So in other words, we can process many, many more sentences. We don't have to say, I'm sorry, I couldn't process this thing. So some of you sort of like asked, geez, I mean, is there a more systematic way of doing this, of doing the NLP processing? And well, this is what we do when we engineer these systems. We make them work as much as we can. So there's not necessarily a systematic way of doing this thing, except you sort of like write code that anticipates many, many different sentence structures and that is able to pick out the things that you want. I point out to you that commands are typically verb phrases, right? Pick up, build, name this, or call it. And so that sort of like helps. But again, how do you know that somebody is naming a block? So if you think about Alexa, how do you address Alexa? You say Alexa, and so that's how the system knows that I need to pay attention now. Well, I need to pay more attention now, right? And so over here, we kind of need to know, okay, so when does somebody actually intend to name a block, right? So we need to look at keywords that they might use. So it's name, call, things like this. And so it's just building it up. I mean, that's what we do. And that's what we do when we engineer the system. It might not be pretty, sometimes a little bit messy, but eventually, we have a system that is able to do many interesting things. Again, we have the confidence aggregator, combines confidence and colors, pointing, natural language processing, and it determines which block is the most likely to be selected by the human collaborator. We have the command unit, pick up, put down, move, grip, things like this. And I already mentioned to you perspective transformation, communication, and then text to speech. So that's it. And so if you're interested in this sort of stuff, there's probably going to be a new project next year where we'll do something interesting. I should say that it took us 3 years to engineer the system. So I say, wow, that's a long time. That's just how it takes, what it takes to engineer systems like this. So we haven't talked much about this, but there used to be the DARPA Autonomous Vehicle Challenge. I forgot when it was. It was quite a while ago. And so they invited research labs to submit their cars for this test. So they had to drive in the desert from LA to Las Vegas. And they weeded out many teams. So I think the final cut was about 15 or 20 teams. And the first time they ran this thing, I think only like a handful of cars actually made it out of the enclosure. I posted some videos of this thing on the day that we covered autonomous vehicles. So I encourage you to look those things up. And those that made it out of the enclosure, I think only one car made it for like, I don't know, 15 miles or something like this out of the, I think it's over 200 miles. And so it was really, for all intents and purposes, a failure, right? I mean, people sort of like thought, wow, we're sort of really hoping to do better on this thing. But, so why did those things fail? Well, they were engineering systems that at the time were probably still running Windows 95, which never ran for more than 3 minutes if you had like more than one process up and running. All right, I'm exaggerating a little bit. But they were dealing with systems that weren't very reliable. And so engineering them just took a lot of effort. So DARPA eventually decided, okay, well, let's do that again. I don't know whether it was a year or 2 years afterwards. And so then things worked out really well. So Stanley was the Stanford entry, and they won that competition. Carnegie Mellon came in second. So if you go to the one of the Smithsonian museums in Washington, D.C., I forgot which one it was. Last time I was there, they had Stanley actually on display. So it was the first autonomous vehicle that of significance, really, that independently sort of like drove from through the desert. So that's what it is. And again, these are research labs. And if you look at the papers about Stanley, I mean, there were like, I think there were like 30 authors. And those are just some of the people that were involved in it. I mean, they had Intel involved, they had VW involved, obviously Stanford. It's just crazy. And that's what it takes. So you're doing real engineering right now by working on that project, on the class project. So continue doing it. Well, that's it for today. I'll see you tomorrow. Bye.